तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, we will continue the discussion on the MOS junction or capacitor. Let me remind you the target that is shown on the slide, that is explanation of the CV characteristics. So far we have discussed a number of ideas and concepts which will help us to explain these characteristics. Let us summarize what we achieved so far. In the last class we explained that for ideal MOS capacitor flat band voltage is 0, but for a real MOS capacitor flat band voltage is given by phi ms minus qf by C naught. Therefore, for ideal MOS capacitor the basic equation for the applied voltage is V equal to psi ox plus psi s, as shown in this capacitor here. Psi ox is the potential drop across the oxide, psi s is the potential drop across silicon. Now this is the equation for ideal capacitor. For a real capacitor, all that you do is you replace V by V minus VFB. Similarly, the ideal MOS capacitor equation for threshold voltage Vt equal to minus Qd inverse by C naught plus phi t is changed to Vt minus VFB equal to the right hand side here. So this is a more general equation for threshold voltage. Now please recall that we are doing all our analysis for p-type substrate. Okay, so unless otherwise stated, we are assuming a p-type substrate and the equations we show will be valid for p-type substrates. Therefore, the expression for Vt can be written as Vt is equal to VFB plus this quantity, which is the quantity for ideal MOS capacitor. It is useful to write this charge in terms of the modulus, because then we will find that we can write the equation very easily for n-type capacitor also. So we can write this equation and then show that just the signs change to negative signs here to account for a capacitor which has an n-type substrate. So here this is p-type substrate that we must note. Now what will happen to an n-type substrate? If the substrate is n-type, then please note here in terms of this diagram, for creating an inversion layer in an n-type substrate, you will have to apply a negative voltage, because inversion layer in n-type substrate means holes at the interface. To get positive charge in silicon, you should apply negative voltage. So for n-type substrate, what will happen is the psi ox and psi s will be negative, because the applied voltage is also negative. So therefore this equation just gets modified to VFB minus Qd inverse by C naught minus phi t. Okay, so here positive sign applies for P substrate and negative sign for N substrate. So notice that this is modulus of the depletion charge at inversion, for which we have written an equation already in terms of the doping. Now coming to the QV relation, this is the QV relation for p-type substrate. Where the charge is 0 for voltage equal to VFB, and beyond threshold you have inversion. Please recall that this line, the slope of this line which is an accumulation, and the slope of this line which represents the inversion charge, both these slopes are the same, because the equation for this is Q accumulation equal to minus C naught into V minus VFB. So we need some more space here. Whereas the equation for this is, this for inversion is Qi is equal to minus C naught into V minus Vt. So please note that if you differentiate this expression with respect to voltage and you differentiate this expression with respect to voltage, you will get the same slope, okay? That would be the capacitance C naught. Now on this diagram, if you want to draw the picture for n-type capacitor, it would be the following. So for n-type capacitor, the accumulation charge is negative, because if substrate is n-type, then accumulation means electrons. So therefore it is simply a reflection of this curve on this voltage axis. So like this, and okay, so this is n-type substrate. So that summarizes our discussion so far. Now before we take up the capacitance voltage characteristics based on this charge versus voltage characteristics, let us explain why this term phi t here in the threshold voltage is also referred to as twice phi f. So what is this twice phi f? To understand this, we should look at the energy band diagram. So look at the energy band diagram at inversion. Supposing I assume a p-type substrate, then at inversion the energy band diagram is as follows. You first draw the Fermi level. In the bulk, these are your bands. Now at the interface, what you know is that the surface concentration of electrons is equal to the bulk concentration of holes. So let us draw the intrinsic level here in between. And now this difference indicates the bulk concentration of holes, difference between EI and EF. So here your intrinsic level should cross this EF and come down, so that the surface becomes n-type to the same extent as it is p-type in the bulk. So therefore your band diagram at inversion would be something like this. So this is P substrate band diagram at inversion. So this distance is equal to this distance. So this ensures that Ns is equal to P naught. Now this difference Ei minus Ef is referred to as the phi f into Q. So Ei minus Ef, the difference between the Fermi level and the intrinsic level, this difference is normally referred to as the Fermi level, phi f, the symbol phi f. Now therefore you see that if you want to know the total potential drop in silicon, on the band diagram this is the total potential drop. So this is psi s. So this is phi f and this is phi f. Now obviously this psi s is nothing but this difference here between this intrinsic level and this point. So this is equal to twice phi f, okay, at inversion. This is phi t. So this is psi s, which we can also call as phi t, and that is twice phi f. Now in our nomenclature what we will do is we will take the modulus of this and call it as phi f, because clearly if you take an n-type substrate, the Fermi level in the bulk would be above Ei, and therefore this phi f according to the definition Ei minus Ef by Q would be negative. Okay, so to avoid confusion we will use phi f as the magnitude of the difference between Ei and Ef. Okay, so this is the reason why this phi t is also written as twice phi f, where phi f is Vt ln doping by Ni. Now this doping could either be acceptor type or donor type. So we can write here suffix A or D, because for both this formula is valid. Now we are ready to discuss the capacitance voltage characteristics based on the QV characteristics. A simple way of deriving the capacitance voltage from the charge voltage is as follows. We can write the capacitance as dqs by dV with a modulus. So this is the so called quasi-static definition of small signal capacitance. The quasi-static capacitance, if you recall in the context of PN junctions, was also the small signal capacitance. So quasi-static also means a small signal capacitance at low frequencies, okay, because this Q versus V corresponds to DC conditions. So when you obtain a capacitance by differentiating DC conditions, it is said to be a quasi-static capacitance, or it is equivalent to saying it is a low frequency capacitance. You are changing the voltage very slowly so that always almost steady state remains, okay, and then you are deriving the capacitance from the changes in the charge because of changes in the voltage. So this is also the low frequency capacitance. So we will indicate this by putting a suffix LF. So if you differentiate this curve, let us take the p-type substrate. You take this curve and if you differentiate this curve, what kind of shape will you get? When you differentiate this, you get the capacitance as C naught. This is clear from this equation. When you differentiate this, you again get C naught from this equation. So in between you have a variation. So you find this slope here varies from C naught and it decreases. As you can see, the slope here is decreasing up to some point and then it abruptly changes to C naught. So this behavior we can plot as follows. So this is C naught, this is a flat band voltage, and this is the threshold voltage Vt. Then the capacitance falls, so this is how the shape is, and beyond this it abruptly rises again back to C naught. So this is C versus V. This is the behavior that we get for the low frequency capacitance from differentiating here like this. Now, what is the meaning of this? The meaning of this capacitance is that when you make changes in the voltage, initially the change in the charge because of change in voltage is coming from the interface, that is why the capacitance is C naught. That is, in terms of this diagram here, when you make a change in the voltage in the accumulation region, the changes take place right at the interface. Now, when you move into the depletion region, okay, this is the depletion region between VFB and VT. This is the accumulation. When you move to the depletion region, you find the capacitance is falling. Now, what is the reason? The reason is as follows. If you look at this MOS capacitor, when the device is in depletion, you are creating a depletion layer, and this is the charge. We are taking a p-type substrate of ionized impurities. When you make a change in the voltage, there is a change in the charge, and that change occurs at the edge of the depletion layer. So therefore, if you take only the changes, you find that the change in charge, there is a change in positive charge at the gate located here, and there is a change in the negative charge in the semiconductor located at the edge of the depletion layer. Okay? So here evidently the capacitance is smaller than the oxide capacitance, because this is the distance between the changes in the charge. That is the incremental picture. Now let us draw the incremental charge picture, okay, for increment in the voltage. So this incremental picture is as follows. This is the oxide layer, and what we are showing is the space charge versus distance, but in the incremental picture. So when the device is in depletion, you have positive charge here at the gate and a negative charge here at the edge of the depletion layer. Okay? So this is for depletion. This is what we explained based on this diagram. Now as your voltage increases, you find the capacitance keeps falling until you come to the edge of the depletion layer, or when you come to threshold. Okay? So what is happening here in terms of this diagram? The depletion width is expanding, and the increment therefore takes place at the edge of this depletion layer. Okay? So for a higher voltage, when you make a change delta V in the voltage, the change delta Q in the charge, delta Qs, takes place at a farther distance from the interface. So this is what is shown here. Okay? The increment in the positive charge is always at the gate here. So this is delta Qs in response to delta V. So this is again another delta Qs. This is for one voltage and this is for another voltage. So supposing you call this voltage V3 and this voltage V4, this V4 is on the verge of just below threshold, okay. So we are following our nomenclature, suffix 4 was always supposed to be near the threshold. So V3 less than V4, this is the increment in the charge. So this explains why the capacitance goes on falling, because this distance between the incremental charges is falling, okay, and this is what is the capacitance. Now what happens beyond inversion, beyond this threshold, you get inversion. Now in inversion the capacitance is rising up to C0. Why? This means that the incremental charges are now coming from the interface. So let us look at this diagram here. What this means is that though you have the depletion layer here, let us say this is a depletion layer edge at inversion. When you make an increment, the increment is coming from the charges here, mobile charges, rather than by the increment in the depletion layer or from ionized impurities, because beyond Vt you are getting a large number of mobile charges at the interface and it is easier to get the increment from these charges. Now since the increment is coming from these charges, your capacitance is again corresponding to C0. So this is what we will show here. So this whole thing is for depletion. For inversion, your incremental picture is this. So this is your delta Qs. So this delta Qs is equal to delta Qd, whereas this delta Qs is equal to delta Qi, change in the inversion charge. So you are not having any change in the depletion charge here. So this is for depletion and this is for inversion. Now for accumulation, let us complete the picture. For accumulation it would be exactly similar to this, except the polarity is reversed. For accumulation you have negative charge in the gate and positive charge in the semiconductor. So this is delta Qs equal to delta Qa. This is accumulation. So that explains the qualitative behavior of capacitance as a function of voltage at low frequencies. Now if you look at the capacitance voltage diagram here, experimental characteristics, you will find the behavior of the capacitance shown by the blue line corresponds to low frequencies. Now here you do not see a very abrupt change of the capacitance, okay, this is gradual. Now this is because the frequency is not low enough. Quasi-static means the frequency is very low, okay, 1 Hz or even less, because the frequency should tend to 0 for quasi-static operation. So such a capacitance versus voltage curve is difficult to measure at such low frequencies. So that is why you are not able to see this kind of that abrupt change going up behavior, but you see that the capacitance in inversion, maximum capacitance here is the same as the capacitance is accumulation. Here we have plotted C by C0. So since C is equal to C0, C by C0 is 1 in accumulation and in inversion. Now what we need to explain is why is it that for high frequencies the capacitance does not go back to C0 but saturate at the point where it comes to at the edge of the depletion layer. Okay. Now let us explain why this happens. Now once the capacitance is in inversion, if the frequency is high, then you cannot provide changes in the mobile carriers at the interface very easily. This is because the mobile carriers at the interface in inversion are minority carriers, and you recall our discussion of majority and minority carriers. We had said that minority carriers are thermally generated. Okay, the majority carriers are derived from the ionized impurities, but minority carriers are obtained by thermal generation. Now therefore, to generate the required number of minority carriers, it takes time. If you change the voltage very fast, then you are not providing sufficient time for the minority carriers to be generated. Therefore, if you make a rapid change in the voltage in inversion, then your change in charge cannot come from this inversion layer, but the change in charge has to be there, because when you change the voltage, there is a change in charge on the gate. Now that change in charge which is required to compensate the change in charge in the gate in the semiconductor, that compensating charge in the semiconductor therefore comes from the edge of the depletion layer, because you can change the majority carrier charge very quickly. Okay, so you can easily get charges by moving the mobile majority carriers away. It is difficult to get change in charge by moving the mobile minority carriers, but mobile majority carriers, they can be very quickly changed in concentration. Therefore, at high frequencies, the change in the charge in response to the change in the charge in the gate comes from the edge of the depletion layer. This means that in inversion, this is the picture at low frequencies. Delta Qs equal to delta Qi. Okay, this happens at low frequencies, but at high frequencies it is not this, it is here, delta Qs equal to delta Qd at high frequencies. That is why if you see the capacitance voltage curve, then as shown here, your capacitance voltage curve will just stop changing beyond threshold, because the charges are now, incremental charges are coming from the edge of the depletion layer, which means the capacitance therefore saturates to the value at this point, because the edge of the depletion layer is not changing much in inversion. Okay, the depletion layer is saturating. Okay, the width of the depletion layer is saturating. So here we can therefore put, this is low frequencies and this is high frequencies. So in between, when you make a change from high to low frequency, of course you will have a gradual change. So say something like this, like that. Okay, now that is exactly what you find. This is what you find in this slide here. So you find when you change your frequency from high value to low value, progressively you are getting these curves. Of course, what you find is that the minimum here is not the same as this value. Okay, so we will not bother about such minor such details, because to explain those you will have to go into more rigorous theory. So here all that it means is that if your capacitance is not really low frequency, your curve may actually come like this and go up. So this is our capacitance versus voltage behavior, qualitative terms, high frequency and low frequency. Okay. Now, what is the expression for capacitance versus voltage in depletion? Because here, to complete the picture, if you want a quantitative analysis, we must have an equation for this curve C versus V. Then we can easily get all the parameters of this particular capacitance versus voltage curve. So that is the next topic, derivation of the expression for capacitance as a function of voltage in depletion. So CV behavior in depletion. So we start with the equation for charge versus voltage in depletion, that is here. This equation for charge as a function of voltage is V is equal to Qs by C naught with a negative sign plus Qs square by 2Q epsilon S Na. This is for an ideal capacitor. For a real capacitor, you subtract flat band voltage from here. Now it is useful to write this formula in terms of the modulus. So when you take the modulus, you can remove this, because you know that when you take a p-type substrate, these two equations, these two terms are both positive. They represent the potential drop in the oxide and in silicon. Now starting from here, we need capacitance is given by d of Qs by dV by our quasi-static approach. Now here you will find that since the voltage is known in terms of the charge on this side, a simple approach to derive this capacitance would be to differentiate this equation with respect to charge, so that we get dV by dQs, that is 1 by C. So when you do that differentiation, you will get dV by dQs is given by with a modulus. That is why we are using a modulus here. You can use a modulus here also, because it is a square, does not matter whether Qs is positive or negative. So when you differentiate, you will get here 1 by C naught plus differentiation of this would be 2 times Qs upon 2Q epsilon S into Na. Now you recognize the fact that this Qs, modulus of Qs is nothing but Q Na into Xd, where Xd is the depletion edge, width of the depletion layer in the MOS capacitor. So this is your MOS capacitor, this is your depletion layer, and this is your Xd. Doping, this is a p-type substrate, so doping here is Na. So Q Na Xd represents the charge here, depletion charge. So you can interchange Qs and Qd, because in depletion the charge in silicon is the depletion charge itself. This being the case, you can write this as 1 by C naught plus Xd upon epsilon S, because 2Q Na and 2Q Na, this will cancel, and this is what you will get. Now you can identify this Xd by epsilon S as the capacitance associated with this depletion layer. Okay, so this is T naught. So you have a capacitance associated with this oxide layer, and you have a capacitance associated with this depletion layer, and both are in series. Okay, so this is C naught, and you can call this capacitance as Cs, the capacitance associated with the semiconductor region. So therefore we can write the same thing as 1 by C naught plus 1 by Cs. that is the overall capacitance. Now still we need to know this Cs as a function of voltage. C0 is constant. To know the Cs as a function of voltage, we need to know Xd as a function of voltage. Now Xd as a function of voltage is actually given by this formula, where you can replace Qs by Qna Xd. So when you do that, what will you get? You will get V minus VFB is equal to Qna Xd upon C0 plus Q square Na square Xd square upon 2Q epsilon S Na. So here we can cancel Q and Na, and then we get, you divide both sides by Q times Na, now you get this equation. So this gives you Xd as a function of voltage. Now what you should do is, you look at this and then you can try to express Cs as a function of Xd in a simple way as follows. Supposing you square this equation, okay, you square this equation, which is same as squaring this equation, then what will you get? You will get 1 by C square is equal to 1 by C0 square plus 2 Xd by C0 epsilon S plus Xd square by epsilon S square. Now you have Xd and Xd square terms here, like you have here. It does not take much time to see that if you multiply both sides by 2 and then you divide by epsilon S, then this quantity is what you have here. You can cancel the 2. Since this quantity is this, we can therefore get the equation 1 by C square is equal to 1 by C0 square plus 2 times V minus VFB upon Q Na epsilon S. Okay, so this is your equation for capacitance as a function of voltage. You can write this equation in a straightforward manner as C is equal to C0 by square root of 1 minus 2 V minus VFB into C0 square by 2Q epsilon S by Q epsilon S Na. That is the formula for capacitance as a function of voltage. Please check that according to this formula, as your voltage increases, this term increases. But then since there is a negative sign, the whole quantity will decrease and capacitance will increase. So this is not really correct, it should be a plus sign. Okay? So one must always check the formula by logical reasoning, whether it shows the behavior correctly and whether the positive and negative signs are correct. We must also check dimensionally. Let us make a dimensional check of this formula. So here this should not have any dimension because you are adding 1 to this, then left hand side and right hand side will have the same dimensions. So here let us write the dimensions of this term. So V minus VFB is volts, C naught square is farad square by centimeter power 4, because C naught is farad per centimeter square. Then Q is coulomb, this epsilon is farad per centimeter, and this doping is per centimeter cube. So you have this cancelling here, this farad cancels with 1 farad there, and farad into volt is coulomb, so this cancels. So now this means that this term is dimensionally correct. From here we can also get what is the value of the capacitance at threshold. So at threshold, all that you need to do is you must substitute Vt for this voltage V. Now this completes the capacitance versus voltage characteristics. Okay. It is now time for a solved example. Let us do a simple example to illustrate some of the ideas that we have developed. Explain the critical capacitance and voltage values on the experimental CV curve shown. You are given that the MOS capacitor has an aluminum gate for which phi m is equal to 4.1 volt, an oxide thickness of 0.2 micrometer and doping level of 1.45 into 10 power 16 per centimeter cube acceptors. So phi m here is the work function. Let us take a close look at the capacitance voltage characteristics. What are the critical values on this curve? So we will draw this curve on the board and mark the critical values from this slide, and we will try to explain them. So the CV curve is something like this if this is high frequency, and if it is low frequency then it goes up and this is low frequency. So the critical values here will be, if you sketch C by C naught versus V, this value is 1, this is known, then this value, this is another critical value that we have to explain. So let us call the capacitance at this point as C suffix t, because the voltage here is the threshold voltage. So here this is Ct upon C naught. So this is another critical value that we need to note from our experimental characteristics. Then this is the flat band voltage. So the critical parameters that we need to explain are this threshold voltage point, that is the value of the threshold voltage and the value of the capacitance at this point, and then the value of the flat band voltage. If you look at the CV curve on the slide, we obtain the value here to be close to say about 0.68 or 0.69, okay, say 0.685. This is the ratio of the capacitance to the oxide capacitance at the threshold voltage point. Now what you note is that the threshold voltage is more easily noted from the low frequency curve than from the high frequency curve. This is because it is difficult to know where exactly it has stopped changing, okay, or where exactly it is saturating. Whereas in the low frequency curve you have a sharp change here which enables you to locate the threshold voltage. Now this threshold voltage is approximately about 1 volt. So let us mark those points here. So we want to explain that why this is 1 volt and why this value, which is Ct by C naught, is 0.685. So this Vt we are able to locate from the low frequency curve rather than from the high frequency curve. That is the advantage of the low frequency curve, that it enables you to locate the threshold voltage point rather precisely on a CV plot. Now what about the flat band voltage? Let us look at this curve. Now like it is difficult to locate the threshold voltage on the high frequency CV curve, it is difficult to locate the flat band voltage on the CV curve. Both low and high frequency CV curves at flat band point and below flat band point are same. This is because you really do not know where the curve has started increasing. Though we have shown the flat band point to be somewhere here, you really cannot locate it precisely. You can even move it to the right, okay? So we do not know exactly where the flat band point is. So let us try to see whether we can extract the value of the flat band voltage from the other values, that is the threshold voltage and the value of the capacitance at threshold. From these parameters whether we can extract the flat band voltage. Let us start with the threshold voltage. The expression for threshold voltage is Vt is equal to flat band voltage plus square root 2q epsilon s Na into phi t upon C naught plus phi t. Now we are given the value of the doping level. From here we can also get phi t, because phi t is equal to 2 Vt ln Na by Ni. Now for Na equal to 1.45 into 10 power 16 per centimeter cube, we have already done the calculation of this quantity and this quantity. So we have obtained phi t to be about 0.36 volts. I am sorry, phi t is about 0.72 volts. And C naught we have already determined to be 17.7 nanofarad per centimeter square for T naught of 0.2 microns. And in fact this is the so called ideal threshold voltage. This we had shown to be 3.98 volts. So now we want to explain why the threshold voltage is 1 volt. That is what is the value on our experimental curve. So clearly this is because of the presence of the flat band voltage, okay. So we have the relation 1 volt is equal to flat band voltage plus 3.98, from where we obtain flat band voltage is equal to 1 minus 3.98, which is minus 2.98 volts. Now we need to see how we can explain a flat band voltage of this value. So the flat band voltage formula is given by phi ms minus Qf by C naught. Of which we can determine phi ms from the fact that the gate is made of aluminum. So to determine phi ms, let us draw the band diagram. So this is the Fermi level in metal, this is the E naught level. We have been given this quantity is 4.1 volt. So in terms of energy, you will have to multiply it by Q. So what we are sketching is the potentials. Now on the semiconductor side, suppose this is the oxide layer. On the semiconductor side, you know that silicon has electron affinity of 4.05 electron volts. So here it is in volts. So this is chi, this is EC, this is your EV, and this is the intrinsic level, and Fermi level is here. It is a p-type semiconductor. Now this difference is phi f, which is half of phi t. Now this phi t is 0.72 volts, therefore this phi f is 0.36 volts. Now to determine phi ms, this is phi m and phi s is this quantity. So to get this quantity, we need this value, because we know this value. Now this value is 0.55 volts, because it is half of energy gap of silicon. So now we can put this value and this value together to get this phi s, and then we can get phi ms. So phi ms is equal to phi m minus phi s, that is 4.1 minus 4.05 plus 0.55 plus 0.36. Now this value turns out to be 0.86 volts. So phi ms, this quantity is 0.86 volts. Flat band voltage we want to explain is minus 2.98 volts. So obviously now incidentally phi ms is negative, phi m is 4.1, this is actually negative. Please note phi m is less, phi s is more. So but still you cannot account for this 2.98 only from phi ms. So obviously there is a fixed charge Qf. Now what is the value of the fixed charge? We can write Qf by C naught is equal to 2.98 minus 0.86 volts, this is 2.12 volts. So Qf is equal to 2.12 into 17.7 into 10 power minus 9 coulomb per centimeter square, because volts into farad per centimeter square is coulomb per centimeter square. Now this is equal to 3.75 into 10 power minus 8, I am sorry, coulomb is C, coulomb per centimeter square. So this is the order of the fixed charge. It is customary to express this fixed charge in terms of the number of charges. So number of charges is obtained by dividing the fixed charge by the charge on an electron. So Qf by Q, this is so called NF, the number of fixed charges, is equal to 3.75 into 10 power minus 8 coulomb per centimeter square by 1.6 into 10 power minus 19 Now this turns out to be 2.34 into 10 power 11 per centimeter square. So that is the kind of NF which is present. Please note that in the problem you are not given the NF because it is not very easy to determine NF before you make the capacitor, okay, unless your process is very standardized. You do not know. You know the doping level of the starting semiconductor, you also know how much oxide you are growing, but this QF is very sensitive to the way you grow the oxide conditions, oxygen conditions during the oxidation and so on, okay. So that is why this NF or QF has to be extracted by measurement. So having explained the value of NF, now we can explain the flat band voltage. So we have the flat band voltage equal to minus 2.98 here. Okay. So what we are left with now is this Ct by C naught. So let us see how you can get Ct by C naught. We can get it from the formula for capacitance as a function of voltage. So this is the formula for capacitance as a function of voltage. You want the capacitance at threshold. So this is the formula. So we have to substitute the various values here to get the ratio. So we can write Ct by C naught is equal to 1 over square root of 1 plus 2 into Vt is 1 volt, VFB is minus 2.98 volts. So this is 3.98 volts. We must put the units here simultaneously. Into C naught square, that is 17.7 square into 10 power minus 18 farad per centimeter square, square of this. So farad square per centimeter 4 divided by Q is 1.6 in 10 power minus 19 coulombs. So minus 19 goes here as plus 19 coulombs into doping is 1.45 into 10 power 16, that goes as minus 16 over there centimeter cube, and finally epsilon s, this is 10 power minus 12 farad per centimeter. So that goes as 10 power 12 over there farad centimeter. You check that all these cancel and you get a dimensionless quantity. Now you evaluate that quantity and you will get the value to be 0.7. Okay. So therefore here this value we get approximately 0.7 from calculations. So this is how we can explain the critical parameters on the capacitance voltage curve. There are some more aspects of this capacitance voltage curve that we will discuss in the next class.